So this is Unit 5, Integration of Exponential Functions. We're going to look at functions of the form f of x is equal to e to the u times du dx, or f of x is equal to a to the u du dx. So considering a function of the form f of x is e to the sine x times cosine x, assuming we can use u substitution to find the antiderivative, what would be the appropriate substitution, and then what is the antiderivative? Well, we can see that if we set u to sine x, then du will simply be cosine x dx. We can rewrite this integral as e to the u du. We know that the antiderivative of e to the u is going to be e to the u plus c. Substituting everything back in, we have e to the sine x plus c. So antiderivatives of the form e to the u du work out to a fairly simple e to the u plus c as a fairly simple reverse application of the chain rule. So as a result, many of these types of integrals are quite easy to evaluate. Generally, you're going to choose the exponent of e to be your u. So if we have, as in example 1, e to the square root of x over the square root of x, if we set u to the square root of x, then du is 1 over 2 square root of x. Multiply both sides by the 2. We have 2 du is equal to 1 over the square root of x. It's very simple to see then that we have the integral of e to the u times 2 du. Factor out the 2. 2 times the integral of e to the u du, which is then going to be 2e to the u plus c. Substitute in our values, and we have 2 times e to the square root of x plus c. So looking at this next example, and this will have a change of variables and a change of your limit of limits of integration. So we have u, we would set to sine of pi x. Du will be pi times the cosine of pi x. So again, we're going to go ahead and divide through by this pi. Cosine of pi x. Now we're going to go ahead and change our limits of integration. So we have u of 0 is going to be the cosine, is going to be the sine of 0, which we know is 0. U of 1/2 would be the sine of pi over 2, which we know is 1. So then we have 1 over pi times the integral of e to the u du. And we're integrating that from 0 to 1. So we know that this is then 1 over pi e to the u, evaluate from 0 to 1, which then gives us 1 over pi times e minus 1. And there is our solution. Okay, so be cautious of assuming that every integrand that involves an e will antidifferentiate in this manner, as we can see in the following examples. So, with example 2, I can see that it's not going to be an e to the u du type of situation, but if I choose my u to be e to the negative x, du is negative e to the negative x dx, which means I can rewrite this integral as negative of secant squared u du. I recognize that that integrates to tangent, so I have negative tangent u plus c, substitute back in my u, and I have negative tangent of e to the negative x plus c. Now, the I'd like you to try the next integral on your own and see what values you get, and that will be one of the questions at the end of this video. And then let's go ahead and look at this last one together. So I'm going to follow the process that we've been using, where if it's in a denominator, that's going to be what I choose to be my u. So u would be e to the x plus e to the negative x. Du is e to the x minus e to the negative x, which looks a lot like what I have in my numerator. So if I take this function and I factor out a 2, I have e to the x minus e to the negative x over e to the x plus e to the negative x, quantity squared dx, which is indeed what I have. So we can rewrite this as 2 times the integral of 1 over u squared du. I know that this becomes 2 times negative 1 over u plus c. Substitute my u back in, and I have 2 over e to the x plus e to the negative x, and there should be a negative here, plus c. So when you're integrating an exponential form with a base not equal to e, we need to keep in mind that the derivative differentiation of a to the x yields a factor of the natural log of a. Given this, it should make sense that the integral of a to the u du will be 1 over the natural log of a times a to the u plus c. We can also do this using the chain rule as shown. So if we are looking to find f of x such that f prime of x is 3 to the 2x minus 1 and f of 1 is 5, we've got a lot happening in this one. So we're going to start with the fact that we know that f of x is going to be the antiderivative of 3 to the 2x minus 1 dx. Now, again, we recognize that the exponent needs to be our u, so 2x minus 1. du is 2 dx. Again, I know we don't have that in this integrand, so du divided by 2 is equal to dx, which means that we are now have the integral of 3 to the u times du over 2, which means this is 1/2 the integral of 3 to the u du. So this becomes, following the formula, 1 over 2 times 1 over the natural log of 3 times 3 to the u plus c. Substitute in our u, and we have 1 over 2 natural log of 3 times 3 to the 2x minus 1 plus c. So now we need to use our initial condition. So we know that f of 1 is 5, so 5 is equal to 1 over 2 times the natural log of 3, 3 to the 2 times 1 minus 1 plus c. So we have then 3, we have 5 is equal to 3 to the 1, which is just going to be 3. So we have 3 over 2 natural log of 3 plus c, which then implies that c is equal to 5 minus 3 over 2 natural log of 3. And so our final function is going to be that f of x is 1 over 2 times the natural log of 3, 3 to the 2x minus 1 plus our c, as follows. Okay, so the next section is forms of the f of x is 1 over u du. So we've already established that the derivative of the natural log of x is 1 over x. And so it follows that the antiderivative of 1 over x dx is equal to the natural log of the absolute value of x plus c. Absolute value is necessary to satisfy the domain requirements of the natural logarithm function. Given the above, any function that fits the general form of du over u will integrate to the natural log of the absolute value of u plus c, where u is some function of x. So let's go ahead and take a look at a couple of these. So in example 4, we have 4x plus 2 over the square root of x squared plus x plus 5 dx. So again, choose your denominator to be your u, so x squared plus x plus 5. So du would be 2x plus 1 dx. Now we can simplify this numerator as 2 times 2x plus 1 over x squared plus x plus 5 dx. So we should be able to recognize that this is then the integral of 2 over u du, which gives me then 2 times the natural log of u plus c. Substitute in our u, 2 times the natural log of x squared plus x plus 5 plus c. Okay, so let's go ahead and take a look at this next function here. We have the antiderivative of 1 over the natural of x times the natural log of x. So we're going to choose our denominator of natural log of x to be our u. So du becomes 1 over x dx. Now again, we have a definite integral, so we're going to go ahead and change our limits of integration. So u of e is the natural log of e, which we know is 1. And u of e squared is the natural log of e squared, which is going to be 2. So we can rewrite this integral as the integral from 1 to 2 of 1 over u du. We know that this is going to be the natural log of the absolute value of u from 1 to 2, which is the natural log of 2 minus the natural log of 1. Natural log of 1 is 0, and so we are left with just the natural log of 2. All right, let's go ahead and take a look at this next one. We'll set it up, and I will have you finish that one in as part of the video. So again, we're going to choose our denominator to be u. So u is going to be e to the x plus e to the negative x, and you'll recognize this from my previous problem. So du is then e to the x minus e to the negative x. And again, we recognize that we have the 2 in the numerator. So we need u of 0 is going to be e to the 0 minus e to the 0, which will then just be 0. I apologize. That should be a u e to the 0 plus e to the 0, which is going to be 2. And then u of 1 is going to be e to the 1 plus e to the negative 1. So we have e plus 1 over e. That seems complicated, but there's a lot that's happening here. So the last step that we're going to follow is going to be 2 to e to the 1 to the e plus 1 over e of 2 over u du. And I'd like you to go ahead and finish that one for the end of the video. Okay, so the trig functions cotangent x and tangent x can be done in a similar method. So we're going to go ahead and integrate the tangent of x, and I will have you do cotangent of x as part of your video. Now we need to recognize that we can write the integral of tangent of x as the integral of sine x over cosine x dx. Well, this lends itself beautifully to u substitution. Again, choose your denominator to be your u, so cosine x. Du is negative sine x dx. So we can then rewrite this integral as negative of the integral of 1 over u du, which then gives us negative natural log of the absolute value of u plus c. Substitute in your u, and we have negative natural log of cosine x plus c. I'd like you to go ahead and do cotangent x and see what you come up with for that one. And then the last example that we're going to do is this one. So again, we're going to choose our u to be 1 plus x to the 1/3. Du is going to be 1/3 x to the negative 2/3 dx. Again, we recognize I don't have the 1/3, but I do have an x to the negative 2/3. So this becomes 3 times du is equal to x to the negative 2/3 dx. We have a definite integral, so let's go ahead and evaluate this. So we have u of 1 is going to be 1 plus 1 to the 1/3, which is simply 2. And u of 8 is going to be 1 plus 8 to the 1/3, which will be 3. So rewriting this integral, this becomes 3 times the integral from 2 to 3 of 1 over u du, which is going to be 3 times the natural log of the absolute value of u, evaluated from 2 to 3. So this is 3 times the natural log of 3 minus the natural log of 2. Now we can use our properties of logs to simplify this, and this becomes 3 times the natural log of 3/2, or the natural log of 27 over 8, because we can bring the exponent up and cube both of those terms.